Right. Today, we are diving deep into the invisible chemical reactions that are happening all around us, and yeah, even inside of us every single second. We're talking about acids, bases, and salts. And I know, it might sound like a flashback to a high school chemistry class, but trust me, this is the science that literally powers your daily life.
So think about this. Ever had that really uncomfortable, burning feeling after a huge meal? You know the one. We've all been there. But what's actually happening inside your stomach to cause that? Or how about this little bit of kitchen magic? You've got a yellow curry stain, you scrub it with some soap, and all of a sudden it flares up into this deep red color. What is going on there? Well, it's not magic, it's chemistry.
Turns out, the answers to both of these little mysteries lie in the fundamental properties of acids and bases. So come on, let's dive in and really unpack the science behind it all. Okay, let's start with the absolute basics. For centuries, one of the first ways people even started to classify these substances was with a super simple and, let's be honest, a definitely not always safe method: taste. So, on one side, you have acids. Think about lemons or vinegar. They have that classic puckeringly sour taste. On the other side, you have bases, which are the opposite. They're bitter, like baking soda. But beyond taste, they do opposite things to a special dye, called litmus. Acids turn blue litmus paper red, while bases turn red litmus paper blue. It's like a simple but really effective chemical fingerprint. Of course, we can't, and you definitely shouldn't, go around tasting unknown chemicals. So how do we safely tell them apart? Well, we use something called an indicator. You can think of an indicator as a kind of chemical detective. It's a substance that literally changes its color when it's in an acidic or a basic solution, giving us this really clear visual signal about what we're dealing with. And this brings us right back to our curry stain mystery. Turmeric, the spice that makes curry that vibrant yellow color, just so happens to be a fantastic natural indicator. And soap, well, soap is a base. So when you take that basic soap and scrub it onto the turmeric, boom, it reacts and changes color to that reddish brown. Mystery solved.
And there are so many of these chemical detectives out there. Nature gives us tons of them. Litmus comes from lichen, you can use red cabbage juice, even certain flower petals work. In the lab, chemists have synthetic ones like phenolphthalein. And get this, there are even olfactory indicators, which change their smell depending on if they're in an acid or a base. Things like onion or clove oil. How cool is that? Okay, so now we know how to identify them. But what happens when they actually start to react with other things? What do acids and bases really do?
Let's look at a really classic reaction. See here? When you drop a piece of metal like these zinc granules into an acid, something happens right away. You can see all these bubbles just fizzing up and rising from the metal. So what are those bubbles? That's hydrogen gas being created. And there's a famous little party trick to prove it. If you bring a lit match or a splint near the mouth of that test tube, the gas ignites with a very distinct pop sound. That little pop is the signature test for hydrogen. But probably the most important reaction for our story today is called neutralization. This is what happens when an acid and a base finally meet. They basically cancel each other out. And what do they produce? Two very neutral things, a salt and plain old water. And that is the solution to our indigestion problem from the beginning. That burning feeling is caused by too much acid in your stomach. So when you take an antacid, which is just a mild base, you are starting a neutralization reaction right there in your gut. The base neutralizes that excess acid and you start to feel relief. Pretty neat, right? So we know what acids and bases are, but are they all created equal? Not at all. Some are really strong and some are pretty weak. But what does that actually mean, chemically speaking? Well, the secret is all about ions. When an acid dissolves in water, it releases these positively charged hydrogen ions, or H+ ions. And these ions are key because they allow the water to conduct electricity. So if you set up a circuit like this, an acidic solution can actually complete it and light up that bulb. The brightness of that bulb, well, that tells you everything you need to know about the acid's strength. And here's the crucial part. A strong acid, like hydrochloric acid, releases a ton of H+ ions into the water. That creates a strong electrical current and makes the bulb glow really brightly. But a weak acid, like the acetic acid you find in vinegar, it only releases a few H+ ions. That means a weak current and a much dimmer bulb. So it really all comes down to the concentration of those ions. This whole idea of hydrogen ion concentration is so important that we actually have a special scale just to measure it. It's called the pH scale. And this one little concept pretty much governs everything, from the cells in our bodies to the atmospheres of entire planets. And here it is, the famous pH scale. Fun fact, the P actually stands for the German word Potenz, which means power, as in the power of hydrogen. It's a scale that runs from 0 to 14. A really low number means something is very acidic. A really high number means it's very basic or alkaline.
It's actually pretty simple to read. Anything with a pH below 7 is an acid, think lemon juice. Anything above 7 is a base, like a baking soda solution. And right there in the middle, at exactly 7, is perfectly neutral. That's the pH of pure water.
So why does this one little number matter so much? Because pH balance is absolutely critical for life itself. Our own bodies have to stay in this razor-thin pH range, between 7.0 and 7.8. Go too high or too low, and the microscopic machines in our cells just shut down. It's the same for the environment. Acid rain, which has a low pH, can devastate aquatic life. And plants, they need a very specific soil pH just to absorb nutrients and grow. It is everywhere, and it is everything. Which brings us to a much, much bigger picture. Let's think about our planetary neighbor Venus. Its atmosphere isn't made of clouds of water vapor like ours. No, it's made of these thick, yellowish clouds of incredibly corrosive sulfuric acid. And that leaves us with a final, pretty provocative thought. We've just seen how essential a stable, balanced pH is for every single form of life that we know of. So if that's the case, could life, as we understand it, ever even begin to exist on a world as intensely acidic as Venus? It's definitely something to think about.